Hello, my name is Bob D. Hilster, and I am your particle model guru. Today I'm going to be talking about inertia. This is a fifth video in a series of questions, and the topic is going to be inertia. Before I start, if you're new to the particle model, I recommend that you watch these two videos. The particle model overview, which overviews how the particle model explains anywhere from gravity all the way out to chemistry. And then there's the level of the universe, which is an important part of how the structure of the universe as the particle model views it. So if you're new, watch these videos. So I looked up the word inertia in Wikipedia, and this is what you get. Inertia is the resistance of any physical object to any change in its velocity. This includes changes to the object's speed or direction of motion. In fact, velocity is a vector which includes a magnitude, and the magnitude is its speed, and it includes information about its direction. But I highlighted the word resistance because that doesn't seem right to me. I can resist being pushed by someone if I push back, but I need to anchor myself to do that. I need to use the friction of the weight of my body and the friction on the floor to anchor myself, or even a wall. I need an anchor. Then when I push back, I can resist motion. I can resist being pushed. But the question then is, can an object in free motion actually resist against the force that is trying to change its speed and direction? Can it resist when there is apparently no anchor? Well, Newton is really the one who suggested this whole idea, and he didn't use the word inertia, but this is his definition of his first principle. And he states, the vis insita, or the innate force of matter, is a power of resisting by which every body, as much as in it lies, endeavors to preserve its present state, whether it be of rest or of moving uniformly in a straight line. Again, Newton uses the term resisting. And I'm objecting to the fact that an object in free space has the ability to resist of itself. So resisting, I cannot resist an external force unless I am anchored to something. An object in open space cannot resist an external force unless it's anchored to something. So there must be something out there. There must be something in space that anchors the object. Now, a lot of people think space is wide open, there's nothing out there. You can make a whole list of things that are really out there, space dust and others, as well as light and whatever else you might be thinking about. But people have theories. A theory of relativity says that there's a space-time continuum out there. Etherists think that there's this, whatever the ether is out there surrounding everything. So yeah, people think there's something out there, and so the particle model, we in the particle model have an idea of what is out there. And the particle model suggests that what is out there is the G1 particle field. This is the important part of the model that provides the sustaining force. I talked about this a little bit in the previous video. Question 4, what is mass? You could go look at it, but I never really talked directly about inertia. I'm talking about mass in that case. But let's talk about the G1 particle field and what it does. The G1 particle field, particles come at the object from all directions. hitting it left and right, up and down, forward and backward. In other words, by hitting it left and right and up and down, and these forces are equal and opposite in those directions, it's going to maintain its direction. If it's at rest, it's going to maintain it at rest. But if it's moving, it's going to maintain its direction. Forward and backward are not exactly equal and opposite. Backward hits push a little bit more than forward hits, and that all depends on the relative difference in the velocity of the object versus the velocity of the G1 particle, and so you have a bit of drag. But when that ratio is so large, the drag is very small. So I maintain that in general, these forces, left and right, up and down, forward and backward, sustain and keep the object moving there. It's applying a force. It sustains the motion of the object, whether it's at rest or at constant velocity. Keeps its speed and keeps its direction. When an external force is applied, it must overcome this sustaining force. And if it's the G1 force field that provides the anchor, then the force must overcome that. And we'll talk about that in the next slide. But let me at least give some credit to Newton and others. Since we cannot see this force, it's easy to assume that the object itself resists. But how can an object out in space sit there and all of a sudden feel this force and say, oh, I got to resist, I got to push against it? It just doesn't make sense that it has that innate ability built into itself. So, it's obvious, but you can't see the G1 force field. They're moving at the speed of light. What you see is the scattered light that comes into your eye. These G1 particles are flying past you right now. You can't see them. So let's try a little bit of a thought experiment. Place a wood ball and a lead ball in space. Set them at rest with respect to an astronaut. The balls are the same size, but the lead ball has twice the mass of the wood ball. I'm just making a general statement. Now apply 1 Newton of force for 5 seconds to each ball. The question is, which ball moves further and which one has the higher velocity at the end of 5 seconds? Well, the wood ball has the highest velocity. The lead ball has a stronger anchor, because the G1 particle field will hit the lead ball twice as much as the wood ball. That's because the lead ball is more dense. The wood ball has a weaker anchor because the G1 particle field, the G1 particles itself, will hit the wood ball half as much as the lead ball. So the force on the lead ball, it has a stronger anchor. And this is what we experience. An object with a greater mass will resist more than an object with a lesser mass. The two balls, I lost my thought. Let me move on. Inertia and gravity together. When in outer space, far from any other object, an asteroid will maintain its speed and direction because of the G1 particle field. That is, there's a balanced force, left, right, up, down, forward, back, that is sustaining the object. As the asteroid approaches a large object, the G1 particle field changes a bit. It changes a bit in the direction of the large object. There are fewer G1 particles coming from the direction of the large object. This part of the force is called gravity. It's small at first because there's a tiny change in the amount as it approaches. But in all other directions, the G1 particle fields are equal and opposite, and this part of the force is the force of inertia. It's the sustaining force. So the object has a sustaining force of inertia, and at the same time it has the force of gravity from a large object caused by the presence of a large object. This happens with subtle changes in the balance of the G1 particle field. Okay. This is, I just made this drawing just to emphasize the point. This is an asteroid. Out here, you have to imagine these are very large distances. And out in the large distances, moving in a straight line, all the forces are equal and opposite, and it's being sustained by that. And it's going to resist. This is going to resist being slowing down, speeding up, turning left, turning right, turning up, turning down. It's good. These forces keep this object doing what it's doing. But then as the closer it gets, you get a small change in the number of G1 particles. G1 particles passing through the large object are reduced. And this blue line is the length of these lines is not important. The color only indicates that it's less than it was before. And of course, here I show it as close as possible to in its path to this object. And it started before that. You can see it actually bent before that. So this force was starting to be reduced, and then it has a maximum value reduced, and then it gets less and less until finally, back out here, it essentially has very little effect from the large object, and it's back to inertia. This visual of how you can see in your own mind how this object has inertia, has gravity and inertia at the same time, is flying by, this visual of the G1 particles supporting it here and then the changing slightly and slightly until it reaches here and gets a maximum and then changes back until it's back to inertia. This visual is quite amazing. And it's simple to understand. And it's, to me, it's very elegant. This is one of the cases, and gravity in the particle model, whether it's gravity 1 or gravity 2, it's very well organized. As long as you have a nice clean system, one object, one asteroid, things are very well organized and well behaved. Many other areas of the universe are very chaotic, but gravity tends to be much more well organized as long as the objects involved are well organized in a sense. Anyway, it's a very elegant solution, easy to visualize, and this object isn't resisting. Any external force that tries to move this has to overcome that object, and this is what is happening here. This larger object is overcoming the force of inertia that I'm calling the G1 particle field here. It's overcoming that by actually reducing it. Okay, in conclusion, it's the particle model field that sustains the speed and direction of the object. The object does not resist. This is a mechanical mechanism that explains inertia without having to assume that objects in free space can somehow resist an external force. It's supposed to be the word resist there. Again, if you're new to the particle model, I recommend you look at the particle model overview and watch the levels of the universe, or you can go to particle.guru and you will find me and all the other videos I have done. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I will explain more of the universe using the particle model. Thank you for your attention.